Welcome, everyone. We're now doing the second half of the plate tectonics lecture. Again, this is the second portion, which means you're now on plate tectonics part B. I'm going to share my screen and pick up where we left off. We left off on slide 51. So just a quick recap of where we've come until now. The first thing that we did in the first portion of the plate tectonics PowerPoint, again, the one you listened to before this, we covered the intro to plate tectonics. We covered the definitions and the differences between continental drift and plate tectonics. We covered, of course, the two scientists, Wagner and Wilson, who match up with them. Wagner, of course, for continental drift, Wilson for plate tectonics. We went over the important dates, 1912 and 1960, again for Wagner and Wilson. We covered all of their theories. And then we spent a lot of time covering the 2 proofs for continental drift and the 6 proofs for plate tectonics. One of the main proofs, of course, is the Wilson cycle. And what the Wilson cycle is showing us, most importantly, is that we have basically only 2 things that can happen in plate tectonics. Things can get bigger or grow or open, or things can get stacked on top of each other or collide together. Or converge, right? So obviously using that very specific plate tectonics term. In other words, 1 through 3 of the Wilson cycle are showing us divergence to come apart. Things are growing. In other words, the sea floor is actually growing. And in 4 through 6, oh, 1 second here. There we go. And in 4 through 6, I made myself advance one. On 4 through 6, these pens are very, very specific. We're using convergence. Now remember, I'm naming these 1 through 3 divergence. Sorry, it's so messy. And 4 through 6 convergence. I'm not making you in any way memorize the 6 different terms. I'm just literally saying 1 through 3 divergence, 4 through 6 convergence. And that's showing us the Wilson cycle. Remember, Wilson is associated with plate tectonics. So the remainder of this lecture, which is now the second half of the plate tectonics lecture, we're going to spend the entire time just focusing on exactly what plate tectonics is, what it does, what it looks like, and what the physical result is on our Earth. In other words, we're going from B to A, right? How did we get from 180 to 210 million years ago during Pangea to the present day? How did things shift? Remember, if we're talking about continental drift, it will appear that the continents drifted apart. But what really happened, you guys know, is that where the plate boundaries meet, a plate tectonic activity occurred and things were either pushed apart, divergence, or piled together, convergence. There is, of course, a third portion, and that's called a transform fault. That's the third section of plate tectonics. So before we go and look at the 3 different types of plate tectonic activities, this particular slide is extremely helpful for you. What it does is it shows a schematic of what Earth would look like if we were perfect, right? If you've ever tried to break a plate, right? If you literally tried to smash it on your knee, you'd never get a straight line, right? It'll break and there'll be a million different pieces of fragments and the edges would be rigid and jagged. Now that's, of course, what happens in real plate tectonics. But just to make it easy for us to understand, we've made these perfect straight lines, okay? So we have 3 plates, plate A, plate B, and plate C. And you want to realize that anywhere that there's a boundary, this would be a plate boundary, something can occur. So I can't say to you, tell me what plate A is doing, because plate A is going to do something different here than here than here. So on these maps, when we look at our plate tectonic maps, we have to literally look where specifically the meeting places are, where the boundary type is. But just for making it easy for schematic purposes, we're focusing on as if we only had 3 plates. Remember, we have 16, 17, sometimes 15, depending on what textbook or person you're asking, but we have definitely more than 3 plates. But regardless of how many plates we have, the Wilson cycle takes over. Only one of 2 things can happen. You can diverge or converge. But of course, like a sliding glass door, if things are shifting in one direction or shifting back in the opposite direction, Then, of course, sliding laterally or faulting at the top and the bottom of the plate boundary. So what that does is it gives us, just as these numbers show you, 1, 2, and 3 types of plate tectonic events. Number 1, divergence. Number 2, convergence. And number 3, which is shown in both the top and the bottom, is your sliding or your transform boundary. What you're noticing here that's happening at the divergent boundary, a gap is opening. New seafloor is occurring. On the opposite side, if plate A is shifting to the left, then it's going to pile up on top of the other half of plate B and cause a convergence. This is going to be an overlap, right? Mountain building, island chain building, mountains in the middle of land. And then, of course, at the top and the bottom, not part of the Wilson cycle, but part of the plate tectonic process itself, would be your faulting at the top and the bottom. So now what we're going to do is literally spend the rest of the lecture talking about the 3 different types of plate tectonic events. Okay, so this is your divergence. Things are going apart. This is your convergence. Things are coming together. And this is your fault or transform, right? Slipping and passing, faulting, or transform boundary. So this is what was represented by C in the figure earlier. This is B in the figure earlier, and this was A, right? Or number 1, number 2, and number 3. Starting first, of course, with the basics. So when you look at any map, and this will be focusing specifically on lab number 2, when you look at any map for the plates are going to be named either as a major plate or a minor plate. You'll notice that a lot of the major plate names, North America, South America, Africa, right? Asia, Antarctica. Those are ones that you know as continents, but there are 7 continents and 5 oceans, and in this list, 16 plates. So do not get confused that a plate is a continent or a plate is an ocean. A plate may include a continent, a plate may include an ocean, or both for that matter, but they're not the same. So the best and easiest way is to take a look at actual plate tectonic maps. Okay, so here all of the major plates are listed for you. If we break that down and actually put it with the water underneath it, because this is oceanography, so it's important to know where the water is, we can now actually see where the major plates are in relation to the oceans, and we've now added minor plates. For example, the Philippine plate, the Caribbean plate, right? There's all little minor plates scattered about. Minor plates almost always have been created from the breaking off of a major plate. Remember, we didn't have 16, 17, 8 plates to start our story. This is over time that things have broken apart. So make sure that you're able to interpret these maps. This particular map is my personal favorite. This is the one that I would recommend that you use to complete Lab 2, and it's the one that I use the most when I'm referencing anything in this PowerPoint or in any lectures that I give. It's really easy and self-explanatory, and it's what we're used to looking at. The land is brown, the water is blue, the plate boundaries are marked very clearly with a black line, and then of course you have your convergence with these little triangles. You have divergence represented by 2 arrows that go apart. So for example, right there. And then you have your faulting as your third plate tectonic activity, and then some other stuff represented for you. Hot spots, which you learned about as one of the proofs. Earthquakes, again, which you heard about as the proofs. So this is a great map to take reference with. Okay? And this is the one that you'll come back to most often in this lecture. You also want to notice that this is not a stagnant or permanent map. Any plate tectonic map that you look at right now can be different tomorrow because, of course, things are moving roughly at 5 centimeters a year, but there's certainly more velocity and less velocity depending on where you are in the world. The Ring of Fire, we talked about that already. You can see that that velocity is certainly a lot faster, and that's also because you have the largest, most major plate of all doing the shifting. You'll also find some interesting activity occurring right on the west coast of the U.S., San Andreas Fault. So what this does is it reminds us that nothing is ever permanent. So anything that you learn today could be different tomorrow, right? Doesn't mean that your answer on a test is different tomorrow. It just literally means that we have 18 plates, or excuse me, 16 plates that we just covered a couple of slides ago. All we need is one more fault, and we have the creation of another plate. So this is an ever evolving and ever changing set of maps. Okay, so let's spend the rest of our time going through our 3 types of plate tectonic activities. Starting first with divergence. This is an easy one. Divergence is also called seafloor spreading. The reason that it's called seafloor spreading is because as these plates open, this portion opens up. In other words, it spreads open. New seafloor, basalt, oceanic crust, will grow from the asthenosphere in that location, literally pushing these plates further apart, and you will literally have new seafloor. There are a couple of scientists that give themselves some credit for this, Hess and Dietz. I don't spend a lot of time focusing on them, but what I do want you to notice is that they come along right around when the Wilson cycle, and Wilson starts in on this. So they work with Wilson in helping him to understand this concept of seafloor spreading. He then renames it more specifically divergence, which is the Wilson cycle correct term for plate tectonics. Continental drift, of course, would be caused by these same forces. In other words, divergence, the beginning of the Wilson cycle, is explaining why continental drift had occurred. Continental drift, again, was just the physical description of what actually had happened. Now here's a good visual again of what divergence looks like. You have your 2 arrows going apart. Remember, transforming can occur at any location, okay? So don't let that stress you out. It's happening there. This is our mid-ocean ridge. It could be a straight line to start, okay? It doesn't have to be, of course. Usually it's looking sort of like a crooked staircase, and that's because you have faulting along the way. But regardless of that, if this were to open up and we started off with a line that's skinny and it opens a little wider, now your seafloor has more room. Let it open a little wider, now your seafloor has more room. And we're literally creating new seafloor, hence it's called seafloor spreading. Another visual, 1 through 3 of the Wilson cycle for divergence. Another visual, same thing. I like to give multiple images. Now on the right and left of this image, this is convergence, so don't worry about that right now. This image, I want you just to focus on the mid-ocean ridge system, the opening and creation of new seafloor, and divergence. Here's the most important part to realize when we talk about divergence or seafloor spreading. First of all, it is caused by the convection current in the asthenosphere. Okay, in other words, the boiling blood underneath the actual crust, which is floating on top of it. If that's the case, though, and we have an asthenosphere that's molten in plastic in this air, which means it's liquid, it's mobile, then we should be able to go to any area where seafloor spreading is occurring and find that they're hot, because of course we have a plate tectonic event, your molten magma is there. The ocean is going to be deeper away from the edges, again, because that's getting further away from the center zone. And the sediment will be thicker in those exact same locations, again, from the erosion where the oceanic crust and the continental crust are meeting. You'll learn more about that as well in the next lecture when we do the ocean basins. So what it's saying that this is older than this, which of course is the case, right? This is time 0. This is brand new seafloor. This could be 90 million years old. Okay, I'm just picking a number. It has to be any time between now and 200 million years old, of course. As you move away, we get older and older and older. Okay. Since the Earth is not increasing in diameter, here is what our action current is looking like. It's explaining to us that, of course, if you have divergence in one location, 1 through 3 of the world, you have to have convergence on the opposite side, or on both opposite sides for that matter. So what it's telling us is that if we have an opening here, and the amount of space that's opening and shifting, that means this whole plate, this African plate would be going that way, North American plate would be going that way. It has to be colliding at some other location on these opposite sides. So it's not like the Earth just gets bigger and bigger and bigger and bigger. It's getting bigger in this location, but that means it's colliding and essentially recycling itself on the opposite sides. It's the ultimate recycling center. So now what I do is just give you a whole bunch more figures, again, demonstrating the same thing, showing you some visuals of where these have occurred, and some really cool pictures, essentially, of where we can find divergence and actually see the mid-ocean ridge above the water. Iceland, on my bucket list to go to, has the mid-ocean ridge, literally, seafloor spreading, occurring above water. That's again because it is pushed so high up that is currently above sea level. Remember, Iceland is an island in the middle of the Atlantic Ocean. So over time, of course, if we get from A to E, we went from old to present day, all we're doing is having that seafloor spreading in all of these locations that you see, allowing this whole thing to essentially spread apart. Your mid-ocean ridge system must match up with the centers of where the actual divergence is occurring. In other words, at any divergent boundary, the geographic or geologic formation must be a mid-ocean ridge. Red Sea, I would love to dive here if I wasn't so scared about the current condition of the state of the world. Another great place that represents divergence. Visual here as well. Pretty cool. Okay, there's your center line. Okay, so that's divergence. Now we're going to go through convergence. Remember, if everything is opening in the center for divergence, 1 through 3 of the Wilson cycle, then it has to be closing 4 through 6, convergence of the Wilson cycle. Now here's where it gets a little bit more complicated. For divergence, it literally just opens. Oceanic crust, new basalt, end of story, not much else to say. We call it divergence or seafloor spreading. With convergence, we have 3 different potential outcomes of how convergence can occur. Because remember, we have 2 different crust types, continental crust or oceanic crust. And if you remember, they're not the same density, and therefore they don't rise and fall based on isostatic equilibrium that you learned from Lab 1. They don't rise and fall in the asthenosphere the same way. So we have to go through each of these individually, but the good news is convergence is the same, right? In other words, it just literally means that something is moving and colliding into something else. We're just going to have different results, different geologic results, depending on what the crust types are of who's doing the collision. So we'll start first with the easy part, okay? Just like divergence is called seafloor spreading, convergence is often called a subduction zone because it means for something to subduct or go under. Particular example here, this one is doing subducting. So if this were plate A is subducting under plate B. That means that this one is the more dense plate. Okay? That's the one that's going to be recycled and burned up essentially and put back into our plastic asthenosphere, and it'll come back out on the opposite side where divergence is occurring. It's also sometimes called a Waddy-Benioff zone. Again, a term that you heard before when we talked about the earthquake boundaries back in the proofs. Again, just because of the scientists that are responsible for it. These are regions, of course, where plates are coming together and it's recycled, so the crust is destroyed. Now remember, we have 3 types, so we're going to go one at a time through each. Type 1, we're going to talk about an oceanic crust versus a continental crust. Now remember, an oceanic crust is more dense, so that's going to be the one doing the subduction. You will then get tectonic event and a violent geologic activity. Okay, so we'll call this plate A, we'll call this plate B. This would be your oceanic plate doing the subducting, causing the earthquake, pushing up the edge of plate B, and this is your continental crust. So it's a continent, oceanic, subduction, or convergent example. What this gives is a trench on the oceanic side, an earthquake, and mountain building on the edge of land. A couple more images of the same thing. Okay, again, always just follow your arrows. Okay, the one that's underneath is the one doing the subducting. Second type, continent versus continent. When you have continent versus continent, we have two equally dense or equally weighted plates. If that occurs, neither is completely subducted. So instead, they're going to compress and uplift, forming a mountain in the middle. This you can remember from lab number 1, the principle of isostatic equilibrium or neutral buoyancy. So what you're seeing here, here's our arrows. So we're showing our convergence or our subduction. But notice you don't have an earthquake, you don't have a trench, you don't have mountains on the edge. Instead, you have mountain building or folding in the dead center of land. Okay, there's no water in this image. Now, it doesn't mean that a tectonic event didn't occur. It just means it wasn't extreme enough for a major earthquake. The Himalayas are the most famous of all mountain building in this particular way. Okay, so again, we're reminding ourselves that if we put more density on here, the displacement changes. So one has to converge with the other. So again, using the Himalayas as our classic example, again, there is an earthquake. It's just not deep focused. No volcano has opened. You then end up with mountain building. So the classic example, the most famous example, again, the Himalayas, is when the Indian plate, which used to be the Indian Australian plate, and now sometimes is called Indo Australian or both, again, depending on what map you're looking at. You have divergence occurring here, which is pushing the Indian plate over. The Eurasian plate is pushing in the opposite direction. Remember, if two arrows are pointing toward each other, one has to subduct, but it doesn't subduct completely. So instead, they pile up and mountain building occurs, known now, of course, as the Himalayas. And there they are. Again, bucket list. Amazing. How great would that be to see? Okay, finally, third type, ocean. So we know that oceanic plates are the most dense. So if two oceanic plates collide with each other, they would be of equal density, except if one is bigger or one is older. Okay, so old or big trumps everything else, and those will be the one to do the subducting. Here, what you'll find, of course, is a trench, just like we did before. Find curved patterns and formations of that oceanic crust, giving you essentially volcanic islands in an arc up at the surface. So here you go. Here's your island arc. Here's your trench. Bigger or older oceanic plate subducts. Other one pushes up, and you get a mountain formation, but that mountain formation is in the middle of water, so we call it an island. If that island is an active volcano, we call it a volcano. Remember, a volcano is still an island. Think Hawaii. Okay, another great visual showing you the same thing. So the trench is going to be on the side of the more dense oceanic plate. The islands will be on the less dense, the one that didn't do the subducting. And finally, transform boundaries. So transform boundaries are what happens. Remember when we had our circle, right? Divergence was here, convergence was here, transforming was at the top and the bottom. So transforming is a sliding glass door, literally. Two things sliding laterally past each other. Most important part, crust is neither created nor destroyed. So density is not an issue. Doesn't mean you don't get a big gaping hole, because we all know what happens at fault lines, but you're not creating or destroying crust. Crust could break off, of course, when a chasm happens, when an earthquake happens, but it's not created or destroyed because of the tectonic event. More specifically, what you're going to find is a violent geologic activity. Okay, so instead of having arrows going apart, representing divergence, or arrows coming together, representing convergence, you have arrows literally going side by side. They're sliding. Nothing is up, nothing is down, like a sliding glass door. They're not bothering each other. Crust is neither created nor destroyed. The most famous of all is the San Andreas Fault. It cuts literally right through coastal California and will eventually fault off Baja. Okay, so the portion of Mexico could potentially change ownership, right? Become an island mass, and where the water cuts through California could also be extremely different in the future. You want to remember, okay, that any time that you have a plate boundary, you can have a transform fault. It doesn't have to occur at a specific location. It can occur during a subduction, it can occur during divergence, and it can occur on its own. So when you go back and you look at all those maps, don't be confused, right? Transform is literally going to be any time that multiple plates are moving simultaneously, things will slide on the top and on the bottom. More close up there of how Baja, here it is, which is part US, part Mexico, could become its own island. All right, so before we go through the summary, I want to go back and touch upon our figures. Again, using the 60 figure as our best and most lucrative place to study. We want to make sure that we can go through this figure and find our 5 different plate tectonic activities. What we're doing, this is for lab number 2. There's a table, and it asks you to fill out the table and give you a divergent example, 3 convergent examples, and 1 transform example. This is the figure that is represented. This is the one I think that you should use. The color one, of course, is better than the one in your lab book. So I just want to use this for you so that you can make sure you understand what you're looking for. So divergence is pretty easy. You're going to look anywhere that you have these arrows. Pick any one of them that you want. Okay, so let's just say, for example, I picked this one. I would then say that my divergent activity is the North American plate diverging from the Eurasian plate. I'm going to get a mid-ocean ridge in the center as my geologic activity and a plate tectonic event. Similarly, it's then going to ask you for subduction zones. Subduction zones are anytime you see these triangles. Okay, so remember, we want to look for triangles in 3 separate spots. One on the edge of land, one in the middle of land, and one in the middle of water, because what that's representing is ocean continent, continent continent, and ocean subduction. In the ocean continent example, the Nazca plate is the oceanic plate converging with the South American plate. What happens? Trench on the edge of the Nazca plate, mountain building, the Andes Mountains, on the edge of the South American plate, and of course, plate tectonic event. Next example, the Himalayas. This is going to be convergent with the Arabian plate and the Eurasian plate. Or, you can use larger plates. It's essentially a bunch of minor plates stuck in between. But the Indian Arabian or the Iranian all can be used, okay, because they sort of attach. This little line here attaches through all of them. Regardless of which ones you pick, of course, what's happening is you're not getting a trench. You're getting mountain building on the edge and an incomplete tectonic event. In other words, not a deep focused earthquake. Finally, if you find island arcs, islands in the middle, you have an ocean subduction. In this case, it would be the Pacific plate and the Philippine plate. Pacific plate, of course, is the bigger plate. That's the one doing the subduction. So a trench will occur. There it is, biggest trench of all. The other one will pop up, and as it pops up all along its edge, you'll get an island arc. Finally, transform. So many options. Just pick any that you want and remind yourself that things are sliding laterally. So going now back to the very end, what I give you is a series of summary slides. All good for you to utilize. What I really like about these is that they give you close-up interpretation, essentially, of where the asthenosphere is in relation to the crust, which way the crust is moving. Again, follow the arrows. So here you have divergent example. Here you would have a subduction example, right? Next example, same thing. This is showing you 2 opposite sides. Again, divergence versus convergence. In this particular case, you would have an oceanic plate and a continental plate represented. This reminds you about the Wilson cycle. Again, don't worry about memorizing all of these terms. We just remember that 1 through 3 and 4 through 6 are divergence versus convergence. the figure that helps you with the scene. So you want to remember, I started this entire set of lecture material by showing you this set of maps from way back in the day. To the time of Pangaea, to present day, to what may come in the future. And I hope you found this really interesting because the topic itself is really, really, really interesting. It's pretty fascinating to think that we're living on these plates that are shifting. Sometimes you can feel it, sometimes you can't, right? Sometimes they cause mass casualty. Other times you have no idea that you're very slowly moving, in our case, moving slowly toward the west. But at any given time, we're reshaping our planet, right? We're literally reshaping what the Earth's surface looks like. So it's pretty cool. The next set of lectures that we'll go through is going to be looking specifically at what happens in the ocean floor. So that'll be next week's set of lectures. And that concludes the plate tectonics.